Hello, everybody. Welcome back. Today we will move to a new and exciting chapter. That chapter will stick with y'all in your transport classes, and it will be a very fundamental things to move forward, to to understand and to apply in any area when you do research or you study anything with fluid mechanics, flow, or heat transfer. Okay, so is the boundary layers problems. The worksheet 21 is posted on Teams, if you can see it. There's two problems. The first one, I will go ahead and derive the formula for you. The second one, I will explain one problems. How do you apply the formula? But before we get started, let's draw some picture and see what we're dealing with. Okay. So let me write. So let's start with a picture. Okay, so you have, let me first draw the coordinate y, o, x. Okay, and you have the velocity profile, looks something like this. Okay, and the velocity profile, I would call it delta, with delta will be a function of x. Okay, and then this is the flow profile, by the way, and then I would take one region, let's say this region right here, one small region right here. I mean, you can take any arbitrary region, but I'm just picking this one because it's kind of like in the middle. I will call this point A, point B, point C, and point D, and we'll do the analysis of this region. Okay, so what happened in this region? Let me redraw it so you have. Okay, let me draw this for y'all. So this is point A, B, C, D. So in the fluid flow region, what's gonna happen? Let's say what force or what type of mass, momentum, or energy flow through it. Okay. So we have flow in and flow out. Okay, this is in and this is out. For the first thing we can consider is the mass. So at a random x point, I'll put this is mass flow rate m dot at x. Okay. Similar here, you have mass flow rate m dot at a tiny point x plus delta x. Okay, this length right here is delta x. Okay, so I pick a random x length. Okay, I say the mass, there's a mass flow in that region, and there's also a mass leaving that region. Okay, similarly with mass, you also have momentum come in. I will denote it by the capital letter m dot at x, and leaving is m dot at x plus delta x. Okay, wonderful. Of course, we also have the shear stress coming this direction, tau w. And on the top, where usually you think about a constant thing, yes, we do have a force interaction there. That's force. We also have a mass and momentum flow from upward. That is m dot 0 and big M dot 0. And this is the what's the word for it? That is the atmospheric. That is the U infinity region. Okay, so on this region right here is U infinity. Okay, u infinity, u infinity. Okay, we just consider a specific region. Everything on the top will be u infinity, or in other words, the mass and the momentum is a constant. Okay, we just interest in the x direction. This is how you this is the simplified model. The x direction things change, in the y direction everything constant. The force acting on it is constant. It's the free surface velocity. Okay, so we need a control volume, right? What is our control volume? Our control volume is gonna be, I will put in red, it's gonna be this. Okay, now this is our control volume. Okay, you have this very nice picture. Okay, so what's next? Let me give you all some definition. So what do we have? Again, m dot means flow rate of mass. Capital M dot means flow rate of momentum. Okay, so how do you calculate M dot and capital M dot? Okay, so the first case you do have is before calculus invented. Maybe this one you encounter in your introduction to physics class if you take it in high school or in college. So let me write normally without any calculus. Your m dot gonna be rho times volume, right? Volumetric flow rate, V, capital V dot, okay? So it will be rho times U times Y, okay? Because the flow rate, the volumetric flow rate is equal to the velocity times distance. Similarly, for momentum, you have it equal to m times v, small v as a vector. Okay, I see. Okay, notation. Okay, I will use u dot because, you know, velocity here we use, I think professor used u dot as the velocity, so I will use u dot like this. Actually use m times u, not u dot, because you already have. Okay, the reason why you need a dot, because you need to specify that is per time. Okay, u of its velocity already have the per time terms in it, so you don't need it anymore. Okay, and m right here we can substitute in this, so it's rho times u times y. You can substitute from above times u, so it's rho times u squared times y. Now this is the basic formula we have, right? Okay. Now, with the introduction of integral and boundary condition, it's gonna be a little bit more advanced, a little bit more complicated, but the idea is still the same. Okay, basically it's saying that y changed over time, so m dot instead of rho times u times y, it will be rho times integral of u times dy. Okay, and y is gonna be from 0 to, I think this delta, right, or sigma, I think it's delta. Let me double check the letter for y'all. Just want to make sure. Linear. Yeah, it's delta. Yeah. Yep. It's delta. Okay. Similarly, your momentum flow rate, capital M dot, is rho times integral from 0 to delta of u squared ui. Okay, this is the new formula. Okay, with the introduction of calculus. Okay. All right. Let's see what we're gonna do. Times in, let me check. Oh, it's 10 minutes already. Okay. So in the next video, I will go over the mass balance and then the momentum balance, and then we should get the complete formula. Okay. Thank you y'all for your attention. I'll see you in the next video.